Hi friends, today I would want to discuss with you a problem which I called as affinity based ranking. To understand this problem, let's assume we have a corpus of a billion images. We also have a black box function f that can calculate the similarity between two images in a millisecond. We are not allowed to extract any features based on the images, nor we can reverse engineer the function f. Now, given such a setup, what we are supposed to do is to build a search engine. What this search engine will do, so a user can give any image to this search engine, and the search engine is supposed to return back the top 10 similar images from the billion images that it has in the corpus. Now, one thing we have to note is that test image that a user is providing may not be present in the corpus. So how will you design such a search engine? Let's just spend some time thinking about it. So if we now think of a nice solution, so what you could do, you could actually pick up every point and compare that point with the test point using a function f, which is allowed, right? Because you can actually take two images and compare them. So with this mechanism, we can literally arrange all the images which are there in the corpus, a billion images, and then we can pull out the top 10. However, if you think about it, this is actually computationally expensive because we are talking of 1 billion images and each comparison is going to take a millisecond. So we're talking of something like a million seconds, which is approximately equal to 10 days. So like every search is going to take around 10 days. So this is not computationally feasible solution. Let's think about it. What's the challenge here? So the challenge is that like we haven't done any kind of processing on the existing images, and hence at the prediction time, we have to compare the test images with everything. Another possible solution that we can think about is to, instead of having like comparison with say n points, let's compare against some k points, some number k of points, which is like where k is much lesser than n. And once you know once we have comparison with these k points, then what we can do is that these representative points, we can go to the neighborhood of these representative points and then pick out the top 10 from them. So it must be evident that like when we're talking about this kind of solution, the complexity depends upon the size of the neighborhood associated with each of the k point and the number k. Now, if we talk about this kind of solution, then there are two key questions that we need to answer. So how do we identify the k points and how do we identify k neighborhoods? It should be noted that if the k points are not representative or they are not like well separated apart, what can happen is that some of the test points may run faster because they may be they may actually zero down on the neighborhood faster, and some of the other test points may take longer time. Similarly, it is also important that the neighborhoods defined by these k points should be sort of equally size. Otherwise, while searching in the neighborhood, we might take longer time. So one of the solutions that can be used to identify both k points as well as the neighborhood of each of the point is a k-means algorithm. So let's try to understand what do you mean by a k-means algorithm. So in k-means algorithm, we select any, like the way we run this algorithm is to start with any k random images among the 1 billion images. So we assume that these are our these are the hypothesis that these are our k points which we are going to use at the prediction time. Now we keep on running the following steps unless we see that there is no change happening in the k images, like k sample point that we are picking up. Now what we do, so if we think about these k images that we have chosen randomly above, so we are saying that let's assume we have made an assumption that these are the sort of chosen k points. Now if the chosen k points are there, we assign each of the other points to the one of the closest k point. Like so for every other image in the every image in the billion image, we find out which of the k points, current supposed k exemplar points, which is the closest one. So what we're trying to do is that in this step we are sort of assigning each image to one of those k points, so like sort of defining a neighborhood. Now with the once we define this neighborhood, what actually happens is that maybe within each neighborhood we can have a different mean point. So whatever we assumed as our current k point might change because of the association with like with the changing definition of neighborhood. So we keep on repeating this step again. Like again, we pick up, we define a new set of k points, and then now we say that all the images are found closer to the newer set of k points, and then we again go back and define the k neighborhoods and again the newer set of k points. So we keep doing this algorithm, as we said, till the sort of like the k point that we have do not change, or like the changes is lesser than certain threshold. Now assuming that we so let's assume we have used the k means algorithm to determine the k points, and within each k points we have defined the neighborhood associated with each one of them. So what will be the computational complexity if we use the k means determined k points at the runtime? So obviously you have the test point, which is now compared against the k identified points from k means to figure out the shortest, the closest, or the most closest image point which is there. So that will take like order k, and then within each of this k neighborhood we will actually compare with all the other points, which is like if the neighborhoods are defined like of equal size or like more or less average size, then it's like sort of order n by k. We should note that this actually can be further improved because we can actually further define k means within each of the neighborhood. So what we can do here is to have a tree kind of a construction where we say that we have first layer, we have k points, and within each neighborhood we have another further k or like l points and so on. And this is like a kind of tree based structure. So this is one of the solution that you can apply, which is using the similarity function as a complete black box. And we are actually having this like once we do this offline processing, so we can also create an efficient retrieval setup at the runtime. Please comment for other solutions which are possible, and I think there can be interesting solutions that we can build up on top of it, and I will try to cover some of them in the later videos. Thank you. Have a great day.